Colligative properties are defined as properties of the solution that depend only on the total number of solute particles in the solution and are independent of the chemical identity of the solute particles. In other words, colligative properties are properties that depend on the concentration of the solution and not on the nature of its contents. Solutions containing non-volatile solutes exhibit the following colligative properties. Relative lowering of the vapor pressure of the solvent, depression of its freezing point, elevation of the boiling point, osmotic pressure of the solution. These properties provide methods for the determination of molecular masses of the dissolved solutes. Let us first discuss the relative lowering of the vapor pressure of the solvent. We know that when a non-volatile solute is added to a solvent, the vapor pressure of the solution decreases. According to Raoult's law, the vapor pressure of a solvent, P1, in a solution containing a non-volatile solute is given by P1 is equal to X1 multiplied by P1 naught, where X1 is the mole fraction of the solvent and P1 naught is the vapor pressure of pure solvent. The lowering in the vapor pressure of the solvent, delta P1, is equal to the vapor pressure of the pure solvent, P1 naught, minus the vapor pressure of the solution, P1, or P1 naught minus X1 multiplied by P1 naught. Rearrange the terms, we get change in vapor pressure delta P1 is equal to P1 naught multiplied by 1 minus X1. In a binary solution, 1 minus X1 is equal to X2. That is, the mole fraction of the solute. Therefore, the lowering in vapor pressure delta P1 is equal to P1 naught multiplied by X2. The lowering of vapor pressure relative to the vapor pressure of pure solvent is called relative lowering of vapor pressure. Therefore, relative lowering in vapor pressure delta P1 divided by P1 naught is equal to X2, the mole fraction of the solute. In other words, P1 naught minus P1 divided by P1 naught is equal to X2. Thus, it can be seen that relative lowering in vapor pressure depends only on the concentration of solute particles and is independent of their identity. If the solution contains more than one non-volatile solute, then the relative lowering in vapor pressure of a solvent is equal to the sum of the mole fractions of all the non-volatile solutes. If N1 and N2 are respectively the number of moles of the solvent and solute in a binary solution, then the relative lowering in the vapor pressure of the solvent, P1 naught minus P1 divided by P1 naught, is equal to N2 divided by N1 plus N2. If the solution is very dilute, then the number of moles of solute will be very less as compared to the number of moles of the solvent. Therefore, neglecting N2 in the denominator, we get P1 naught minus P1 divided by P1 naught is equal to N2 divided by N1. Representing N1 and N2 in terms of their mass and molar masses, we get P1 naught minus P1 divided by P1 naught is equal to W2 multiplied by M1 divided by W1 multiplied by N2, where W1 and W2 are the masses, and M1 and M2 are the molar masses of the solvent and solute respectively. Let us now solve a numerical on relative lowering in vapor pressure. The vapor pressure of pure water at 298 Kelvin is 23.8 mm of mercury. 50 grams of urea, NH2CONH2, is dissolved in 850 grams of water. Calculate the vapor pressure of water for this solution and its relative lowering. The first step is to list the given variables. P1 naught is equal to 23.8 mm. Weight of urea, W2, is equal to 50 grams. Weight of water, W1, equal to 850 grams. Molar mass of urea, M2, is equal to 60 grams. Molar mass of water is equal to 18 grams. Now, according to Raoult's law, the vapor pressure of water for this solution is the product of the mole fraction of the water and the vapor pressure of pure water. Let us first calculate the mole fraction of water. Substituting the given values of W1, W2, M1 and M2, and on solving, we get X1 is equal to 0.983. Substituting this value of X1 in the expression, we get the vapor pressure of water for this solution, P1, is equal to 0.983 multiplied by 23.8, which is equal to 23.395 millimeter. Relative lowering can be calculated using the expression derived earlier. Substituting for P1 naught in the expression, and on solving, we get the relative lowering in vapor pressure as 0.017, which is the same as the mole fraction of the solute. That is, 1 minus 0.983 is equal to 0.017. Let us now look at the next colligative property, that is, elevation of the boiling point. We know that the vapor pressure of a liquid increases with an increase in temperature. When the vapor pressure of the liquid becomes equal to the atmospheric pressure or external pressure, the liquid starts boiling. The temperature at which the vapor pressure of the liquid is equal to the external pressure is known as its boiling point. Let us discuss the elevation in boiling point on the basis of curves showing the variation of vapor pressure of pure solvent and solution as a function of temperature. You know that at any temperature, the vapor pressure of a solution containing a non-volatile solute is less than that of the pure solvent. Therefore, the curve corresponding to the vapor pressure of the solution lies lower to that of the pure solvent. The temperatures at which the vapor pressure of the solvent and the solution become equal to the atmospheric pressure are Tb naught and Tb respectively. The difference, Tb minus Tb naught, is represented by delta Tb and gives the elevation in the boiling point of a solvent in solution. Thus, it can be seen that the boiling point of a solution is greater than the boiling point of the pure solvent. In other words, a solution that has lower vapor pressure needs to be heated to a higher temperature for its vapor pressure to become equal to the external pressure, that is, its boiling point. The boiling point of a solvent changes as the concentration of the solute in the solution changes. But it does not depend on the identity of the solute particles. The elevation of the boiling point depends upon the concentration of the solute in the solution and is directly proportional to molality m of the solute in the solution, or delta Tb is equal to Kb multiplied by m, where Kb is known as the boiling point elevation constant or molal elevation constant, or the ebulioscopic constant. Molal elevation constant is defined as the elevation in the boiling point when 1 mole of a solute is dissolved in 1 kilogram of a solvent. Thus, the unit for molal elevation is Kelvin kg per mole. If W2 grams of a solute with N2 molar mass is dissolved in W1 gram of a solvent, then molality m of the solution is given by W2 multiplied by 1000 divided by W1 multiplied by M2. Substituting this value of molality in the equation for elevation of boiling point, we get elevation of boiling point delta Tb is equal to Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. Rearranging this equation, we get M2 is equal to Kb multiplied by W2 multiplied by 1000 divided by delta Tb multiplied by W1. Thus, we see that molar mass of the solute M2 can be determined experimentally if a known mass of solute W2 is taken in a known mass of solvent W1, and the elevation in boiling point delta Tb is determined experimentally for a known solvent whose Kb value is known. This formula is used to calculate the molecular masses of non-ionic solutes. Let us now solve a numerical based on elevation of boiling point. 18 grams of glucose, C6H12O6, is dissolved in 1 kg of water. At what temperature will the water boil at 1.013 bar? Kb for water is 0.52 Kelvin kg per mole. The first step is to list the variables given to us. W2 is equal to 18 grams. W1 is 1 kg. And Kb is equal to 0.52 Kelvin kg per mole. As we have to find the boiling point of the solution, we need to find the elevation in the boiling point. Substituting the values in the expression for delta Tb is equal to Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. And on solving, we get delta Tb is equal to 0.052 Kelvin. Since water boils at 373.15 Kelvin at 1.013 bar pressure, the boiling point of the solution, Tb, can be calculated as Tb is equal to Tb naught plus delta Tb, or 373.15 plus 0.052, which is equal to 373.202 Kelvin.